Welcome to Everything Distributed. Last time we talked about what could go wrong in distributed system. Let's continue to check what else could go wrong. And then this talk is based on this chapter of a very nice book, Designing Data Intensive Application by Martin. And the chapter name is called The Trouble with Distributed Systems. And I think that in terms of dealing with distributed system, we should think about Murphy's law. Whatever can go wrong will go wrong. So you need to deal with lots of different things, lots of different failures. And then to start with, we need to focus on our model, which layer of abstraction that we are dealing with. And remember my definition, we have collection of entities and some form of communication. And then like for this episode, let's focus on this very simple abstraction, which is the message passing model. We have some machine, and then you can send a message of like any particular destination of your choice, and that's all. And it's a very simple model for internet that we are using today. And even for this very simple model, we get away with like from the underlying hardware, how do we do routing, do networking, that kind of stuff. We still need to deal with lots of different things. And then from the list book, DDIA, design data intensive applications, the author, Martin, mentioned three things: unreliable networks, clocks and timing issues, and also all kind of machine failure, and we call that node failures or server failure, which is not the focus today. Let's focus on the first two. And then let's look at the unreliable network. Here's is a very interesting instance or like experience shared by Coda Hale. He is not even an operation guy, but he has already encountered tons of things that you couldn't even imagine. You have long-lived network partition in a single data center, which is usually very optimized, and then you have like this hardware failure, like switch, or you have like power failure, or like you even have like some truck, like kind of crash into your data center. So anything could go wrong. And in terms of our simple model, what does that mean? It simply means that suppose you want to send some message to the others, and then this message may be lost, may be delayed, or maybe deliver out of order. So that when you design something, you need to take those things into in mind. And then if you know something about computer networking, you can say that, hey, this is not the case, because I know that there's a very good protocol called TCP. I use TCP. It should give me like FIFO ordering. The message shouldn't not be lost. Even though it might get delayed, but like usually not too much. And I can tell you that it's not true, because I based on like Coda Hale's experience, and then based on our experience play with real system, there are lots of things that cannot be fixed by a simple usage of TCP. You may have a transient network failure. Sometimes message can be delivered, sometimes delay just too large, and then you trigger like tons of like kind of failure events, or something that sometimes you have asymmetric links, asymmetric path, so that I can talk to you, but like you cannot talk to me. That's also possible. And then one of the worst kind of worst case of network failures are two group of nodes, two group of machines. They cannot talk with each other because you have some kind of network failure, and then your network is a kind of partition. And these are all the things that we need to deal with, both in theory, in a simple model, and also in practice. And then the next one, which is usually not the main focus, but it's also very important to remember if you want to design something for global scale. And most of the machines, most of the application right now we are using, we need to have a clock for each machine. So right now, everyone have a clock. That's very good. And then the reason that you need to have a clock, because like for many of the protocol, you need to use timeout to trigger some event. And then if you are using application using some public cloud, you also want to ensure some kind of guarantees. You want to monitoring whether the cloud give you the satisfied SLA, meaning that service level agreement, or that in terms of your application, you may want to track the user behavior. You want to record some of the state, or even want to replay your log, and all of this requires some kind of timestamp, meaning that you need to record the time for some of the event or some of the message, so you can apply some of the program logic later. For example, suppose you have you use cache, and then you need to kind of garbage collect something, or you need to renew the data. Everything you need to have some kind of clock in order to develop or write your application. But what's wrong with the clock? The problem of distributed computing, one of the biggest problem is that the clock cannot be synchronized. Okay, so in this case, each machine, that's good, they have a clock, but like at some point of time, some work clock time, everyone will have a different clock. Why is that? Because that clock is like some kind of inherent unit, as some hardware attached to your machine. And then that hardware, like this quartz oscillator, is not really robust. It's like very sensitive to temperature, to how old it is, to like certain vibration, radiation, or all the environment. Sometimes it may tick like very fast or very slow. Basically, you have no guarantee to make sure that every machine ticks right at the same time. Okay? Then you might say that, okay, why don't I just like kind of read others' clock's value? Say that, hey, Lewis, tell me what's a clock, then I will follow yours. But the problem, remember, what's the first failure that we saw, which is unreliable network. So suppose you ask the clock value from me, but like the message, my reply never get to you, or like it gets delayed. How do you know what the current clock time is? And actually, it's a non-trivial problem. Okay. And then like one very simple question for you to think about is that even with a very simple theoretical message passing model, can we get accurate clocks with reliable network with a fixed delay? And then think about it. And then in general, fixing the clock is a big issue. And then the problem in distributed computing is called clock synchronization. And then in practice, most popular protocol is probably the network time protocol, NTP. And then there's also some kind of beta version called precision time protocol. And I think back in 2012 or 2013, Google used a very fancy architecture to build their own time protocol, which is called True Time. And then it's one of the reasons that they are able to build a very amazing merge system called Spanner, which we will discuss later. And then if you don't have this kind of infrastructure, you don't have such a huge money to invest in your clock, your different machine architecture, you can also use logical clock, which provides certain guarantees that are useful for many applications, which we are also going to check later. And then in terms of theoretical or fundamental research, there are tons of kind of upper bound and lower bound. How good can you synchronize your clock under which kind of failure, which kind of network? And then hopefully we will visit some of those like theoretical research as well. Okay. So the takeaway for today is that we saw different kind of unreliable network, and mainly its implication on top of simple message passing model. What's the impact? What's the effect of that? And then I also introduced the notion of clock synchronization, because clock is not accurate, and the way we deal with that is to use a kind of primitive or protocol called clock synchronization. Okay, thank you. That's all for today.